Hello everybody and welcome back to the x86 Hobby channel. In this second video we'll be starting an example project, particularly to see how we use the editor and NASM. As in all our projects, we'll be using the EdlinPro template, a very important part of our projects. And in this particular video we'll be introducing two Linux system calls. Okay, let's get started. Firstly, in this video we're going to use two Linux system calls. In 32-bit Linux, these are executed via the 80 hex interrupt. To use any system call, you must set the values of certain registers before calling this interrupt. Firstly, the write to a file. And the registers EAX must contain the function number, which in 32-bit Linux is 4 for writing to a file. EBX must contain the file descriptor. This is a number that specifies the file you wish to write to. However, what we're going to do is write to standard output, which is the screen, so that is always number 1, standard output. ECX must point to the address where the data is stored that we're going to write the file to the disk, or in our case to the screen. So if we have any message or anything like that, ECX must point to that address. EDX is the length of the number of bytes that we wish to send out. Second, terminator process. This is the second system call. EAX must contain the function number 1, which is the terminate process. EBX should return a code, and normally would be 0, meaning no errors. If there are any errors, EBX will show this. This is actually used in EdlinPro to return errors if there are any errors in opening EdlinPro. But in our case, there should be no errors in our simple project. Okay, so firstly we open up a terminal window, and then we type in the following command to start creating our own project. For the sake of consistency, I'm going to call the file project. Here I'm going to copy template.asm to project.asm. That's the very first thing we do when we start a project. Press enter. Okay, now let's just have a look at the listing for that. First of all, we need to assemble it. To do that we use NASM, and the switch we're using is FBin, which means we're going to create a binary file with no linkage involved or anything. The output file name will be named project, no extension, and the input file is of course project.asm. That's our script, our text file, and at the moment that only contains the template, and the template only contains the header of the file. So when I press enter, complete. Now let's have a look at the listing. Okay, to do that we list, and we see, if you look at it, that it's actually only 80 bytes in size. This shows us that template that contains this header is actually only 80 bytes in size. The only time it increases beyond 80 is if we use the debug feature of breakpoint, but that comes much later in the videos. Normally it's always 80 bytes in size. And since project only contains the header, that's all the size of the file is. Okay, so now let's open project.asm with our editor. So we type EdlinPro project.asm, press enter, and we've opened it. Before I continue, I'm going to make this slightly bigger so we can see more clearly what's happening. Okay, now all we have in our project at the moment is the template. Let's have a look at that. Let's move our cursor down so we can see it all. This is the full scale of the template, 32 lines altogether. The first part of the template is the ELF header, and the rest of it is what we're going to add. Now there's a few items though, in addition to the header itself, which are quite important, and I wish to point these out to you. The first one is the flag that enables the breakpoint code to be inserted. Now if you notice, we have the flag which can change between a patch and a $, and if it's set to $, it means we include the breakpoint, which is called break32 in our case, the breakpoint code. This enables us to use breakpoint in our system for debugging. Now this is changed automatically. This flag is changed automatically by Edlin Pro when it's saved. If you've used breakpoint in Edlin Pro, this flag is set to $, and that enables the script. Now without the breakpoint, as we said before, the header generates 80 bytes, and indeed if you were to assemble this, that's all you'll get, just 80 bytes of code. Now if you include the breakpoint, a breakpoint in your text, then Edlin will automatically insert this extra break32 assembly script. That will increase the size of the binary file by exactly 600 bytes. So the header is normally 80 bytes, but if you include that, it's 680. Note, this this flag can only be changed by, or should only be changed by, the Edlin Pro. Don't change it yourself. You should never ever need to go into this header where it's boxed off here. You should never need to change anything here. Secondly, I'll point out one or two important addresses. Again, these are inserted into the header automatically. You should not need to change them, nor should you edit or change any part of the template. The first one I'm going to mention is the start address. Now as you can see, I'm using _start, which is a standard sort of label for starting, very common in C++ coding. But in fact you could use any label here, as long as what's in the header matches what's actually in your script for starting or where the start is of your code. That is the start address. No reason to change it, leave it at _start. Secondly, you'll notice we only have one program header, and this contains all the information we need for our program. We only have the one section, so no need to bother with code section or data section, text section, nothing like that. We just have the one single section. Very important to understand this. Then we have a couple of memory addresses. First of all, we have the top of memory, TOM, top of memory address, which is contained within the header, and of course it's included as part of the program header. Again, no need to change this, just leave it as it is. The next two addresses are the end of memory address and the end of file address. The end of memory address, EOM, is the end of the total amount of memory that you're requesting from the operating system to run your program. And you'll see this is right at the very bottom of your script and should be on the very last line of your script. No matter what you put in it, that should always be on the very last line of your script. Never put anything after that. The end of file address is just before the BSS section, before we put the BSS data. That's the end of file address. Don't get these two confused. As long as you don't touch these normally, no need to, when it says part of the template, just don't touch them. Just put all your BSS information between EOF and EOM after the section BSS, and you should have no problem. Next we have the flag setting for the one and only program, section, and that is flag which is set at 7. This means it's read, write and executable. So the whole of your program is read, write and executable. Okay, so we don't have any separate sections for these, they're all in one flat memory model. Okay, so therefore, where I've shown here, that area there is entirely available for data and code. That is data, predefined data that you need to access, as we'll see in the example I'm going to give you, and the code that's going to use that data. In this particular video, we'll not be talking about the BSS section just now. We'll talk about that in another video. So just concentrate on this first section, which is read, write, executable, and we'll put all our data and code in that section. Okay, now in this simple project example, we're going to write an hello world. So the first thing we do is type in the data that we need. Now what I'm going to do here, I'm going to place a line feed at the end and a line feed at the start. This should help to show it a little more obviously what we're doing. This is of course not necessary particularly, but a line feed which is 10 decimal or 0A hexadecimal. And then next, what I want to do, I need to define another label or another token which defines the length of the message, the number of bytes we actually want to write to standard output. And to do that we use the $sign, which means the current cursor position or current position of the assembled output, which is the very next byte after the last line feed, minus the address of the message. The difference between that is the total number of bytes in that first data block. Okay, let's start writing our code, starting with in EAX we need the number 4, which is write to a file. In EBX the file we're talking about is in fact the standard output. It's actually the screen itself. We want to write to the screen, so we have the standard output number 1. Then in ECX the address of the message itself, or the block of data we wish to write, which is of course message. Then in EDX the length of the message, which we've already defined, so we just move EDX message length. And finally the interrupt itself, which should write out the message to screen. Now of course we need to quit the program, so we have to move EAX 1, EBX 0 meaning no errors, and then another interrupt 80H, which will then tell the operating system that we've finished, we quit the program. So let's see how that runs. First of all, of course, we need to assemble it with NASM. So what I'm going to do, I'm going to press Alt K, and if you remember Alt K, we'll save this and quit the program. Okay, next we'll bring in NASM, and if you remember what we did with NASM, we worked on our project and the output file itself, the binary file, is called project, and if we press enter we should have no errors. That's great. Now let's just see what the size of this file is. To do that we list project with the long output, and we see it's 128 bytes, which shows you that apart from the 80-byte header, we have 48 bytes of code actually running. Now let's try running the program. However, before we run it, we must make sure it is executable. In Linux we can do this very simply so we just change the mode to executable for project, and it should be executable simply by typing its name on the command line. Okay, let's run the program. Project, and there we go, hello world. so it works well enough. Let's go back to the editor, go down to where we were. Okay, we can see this works well. Now, before I continue, I'm going to change these instructions a little bit. If you remember, this generated 48 bytes in as well as the header. Now, in these micro executables, we try to make the best use of the registers that we can. In other words, to make it as efficient as possible. To this end, I'm going to introduce you to a couple of concepts. Now, I want to talk about optimizing the code with register contents awareness. This really is the essential part of our micro ELF executables. And what we mean by this, that is, knowing what a register value should be can help optimize the coding. That doesn't mean to say you should understand exactly what's in every register at every given point in time, but essentially the most important thing to know is when it's clean. I use the term clean to define a 32-bit register with less than a value of 256. In other words, the value can be fitted in 1 byte. This actually can also apply to 64-bit registers, as we'll see in later videos, but since we're dealing with 32-bit, we'll stick with these registers. So a clean register is one that has a value in it that can fit in 1 byte, less than 256 in value, but it's a full 32-bit size register. That can be very important in optimizing the code, as we will see. We can then decide how to code knowing the state of the registers. And we're going to see an example of this in a minute. This is particularly relevant to values before and after the system calls, as we will see. Knowing what the register should be before the system call, of course we've already been through that, but also knowing how those registers changed, what's in them after the system call, can help in optimizing the code. In Linux, all general purpose registers are zeroed by the operating system before starting the execution at start. That is, they are all clean. They're all 0 when the operating system hands over the execution to your program at the start label. Also, the BSS space is cleared, zeroed. Now at the moment that will not affect us in this example because we're not using BSS space, but if we did, it can be very useful to know that that space is zeroed when the operating system gives you that memory available for you to use. Now, the reason for this is for security, but it can be very helpful to us in knowing what to do with register values. Okay, let's go back to our terminal and run Edlin Pro again. Let's have a look at our project. Okay. Remind ourselves what we're doing here. There's our piece of code, short piece of code, and now what we want to put into play are the changes that we need to make to optimize the code as per the last slide. So let's start line by line by line. Now this first one, move EAX4, that normally would create a 5-byte piece of code. 1 byte for the opcode and 4 bytes for the value, because there are 4 bytes in a 32-bit register. However, knowing what we know, we can change this. If you watch carefully, I'm going to say move AL. Now I'll keep it in uppercase letters, so we're using that. Move AL 4. This has exactly the same effect as moving EAX4, simply because at the start the operating system ensures that all the registers are 0. And it's the same with EBX. We could move BL1, but instead of moving BL1, which is a 2-byte operation, I'm just simply going to increment EBX. starts at 0, incrementing it changes it to a 1. And increment EBX is a 1 byte operation. Now, ECX here, the message address, there's not much you can do about that. It is an address, it's a 5 byte operation, not much we can do about that one. Unless for some reason or other we had some sort of index linked with a register indexing it, then there's nothing we can do about that. So that is with EAX message. EAX would have to remain dirty in that case. However, moving EDX, we can do the same as we did with EAX, and we can then move DL with the message length, because we know the message length is going to be less than 256 characters, as we can see at a glance. So we won't get any error from NASM. Now if that message length was much longer than that, then NASM would give us an error, you cannot put that into DL. But in our case it can. And again, it's a 2 byte operation. Now it's important to understand that assuming this is successful and we execute the interrupt 80H, the service, then what do we have after that? Well, after we've done a service 4, AL4, interrupt 80, if it's correct and then there's no problem, then EAX should contain the same value as EDX. EAX should contain the same value as EDX. So in other words, it should be message length, which we know is a 1 byte operation. In other words, EAX is clean when we leave this particular instance of the request. So now we can do the same as we did before, move AL 1. Move AL 1. 2 byte operation does as well. EBX we want as 0. Well, we know that EBX doesn't change in that first interrupt, so EBX is 1, we change it to 0. All we have to do is decrement EBX, and that's 0. Now while I'm at it, I'm just going to press home a couple of times, and let's go over to our comments. Basically what I need to do here is just say what this does, which is output to standard output. The message. Now I'm going to use an ellipse, which I do all the time here. Press enter, keep pressing enter till you finish that little part of the block, another ellipse. In other words, I've grouped all those together, and that's what all those instructions do. And then the final is quit. Okay. There we go. And that's complete that. And we've shortened, or we should have shortened it quite considerably, and still had the same effect, still the same. Okay. So let's save that, and I'm going to save that by pressing Alt K. Now remember, Alt K saves and quits. Now the next thing you have to do, of course, is, okay, we need to make it executable. So we're working on our project, so make that executable, that's fine. And then finally we need to assemble it. So again, we're assembling it in flat mode. The input is project ASM and the output is project. Okay, actually I changed that mod a little bit too soon. I should have done the NASM first. Okay, so let's just do the change mod again. There we go, my mistake. There we go. So, and now if I do a listing, ls project, giving it the full listing, we see that it lists okay, but notice before it was 148, now it's 111 bytes in size. 37 bytes less than it was before. Okay, let's run it. There we go. Hello world. So that's how we clean that up a bit. Now the Edlin Pro itself is also written in this, what I call the micro ELF format. It's only 2.5 kilobytes, and I will be publishing the source code for that, the script, the assembly script, in one of my next videos. Meanwhile, that's all for this video. See you again next time. Thank you for watching.